So when we think about the Internet of Things, and if you look at the kinds of think pieces that come out of the various organizations and analytical groups, this is usually the picture that we see, right? We have materials, devices, systems, and then networks. And of course, we do a lot of work on those topics here at Oregon State, and you've heard about some of the coolest of that this morning. But I'm going to sort of hide all that and just replace it by one line, which I'm going to refer to as sensors. And I apologize to my EE colleagues for simplifying that. But what we want to do now in this talk is to build on that a hierarchy of analysis. So we're going to focus in this talk on data analytics and what we would want to do with those signals, assuming that all of the materials, devices, systems, and networking, that it's all working beautifully, and that our colleagues have solved that. Now, what can we do with the data feeds that we're getting out? Now, at Oregon State, we've built quite a strong group in analytics, and so we're well known across the country and the world. We hosted, for example, the International Conference on Machine Learning a few years back. So most researchers in machine learning have been to Corvallis, at least in the summertime, where they were very happy. And so you've met a lot of these people today in the flash talks. So I won't belabor it a whole lot. But I think what I want to do now is sort of build up from the bottom the different kinds of analytical questions that we need to answer, and then give a few examples of the kinds of things we're doing here on that. So one of the sort of thankless tasks in data analysis is data cleaning. If you talk to most people in industry that work on some large analytical project, they'll say that they spend 80 to 90% of their time doing data wrangling and so on. And so it's not very glorious, but it's an essential step. And we've been doing some research here for the last decade in automated data cleaning. Most of what we've been doing is looking at data that comes from the H.J. Andrews experimental forest, which Xiaoli Fern mentioned earlier, where we've also been doing the bird acoustics project. But as she mentioned, we have a very heavily instrumented forest there. And in fact, ecology, right? Oregon State University is probably the #1 or #2 university in the country in ecology. Our ecologist friends would like to instrument every bee, as you know, every tree, every fish, every flower, so that they could learn about the Internet of living things. In any case, we've been working only with weather data, and if you think about it, weather networks are probably one of the biggest existing sensor networks. That's redundant, but that we have. So we have quite a long experience with them and the problems that arise. Another project that is in its early phases is something called TAMO, the Trans-African Hydrometeorological Observatory, which our colleagues in biological and ecological engineering are involved in rolling out a network of 20,000 weather stations across the continent of Africa. And so the techniques we're developing here, we want to roll out onto that network. So what are the problems? Well, if you look at just the thermometers on one of these weather towers in the Andrews, there are 4 thermometers placed at different heights above the ground. And sometimes you'll get a failure. So the black trace here is actually the sensor that is closest to the ground. So it is coldest at night and hottest in the daytime. But this particular sensor is rather excited in the daytime. Those spikes are not correct. In fact, what's happened is that the sun shield has fallen off of it. So it's no longer measuring the air temperature, it's measuring the skin temperature of the thermometer. And this is true for a lot of sensors, is that when they break, in some sense, it's just the semantics that breaks. If you have you're taking water temperature with a water temperature sensor and the stream level drops low enough, you're now taking air temperature. Or if the snow level goes up high enough, you're now taking snow temperature instead of air temperature. So you could say it's just a problem with the metadata being wrong. The thermometer is still reporting exactly what it's sensing. But that's maybe semantics in a quite deep sense. So what do we want to do? We want to detect bad data values. We want to detect broken sensors. And then if we have models available, we may be able to interpolate from nearby sensors, for example, the other thermometers on this tower, what the thermometer probably would have read. And that interpolation or imputation, it's called in statistics, might then allow subsequent analysis to go forward. So now once we have cleaned the raw data signal, what do we want to do with it? Well, the next level of analysis, one could argue, is state variables. In the forest, we're interested in temperature and atmospheric pressure, but I'm going to shift gears now and think about a kind of high-end retail setting. So I'm thinking Nordstrom's maybe, or maybe Home Depot. And in that case, maybe we want to be tracking the location of each customer in the building, the location of each employee in the building, maybe the total time the customer's in the store, maybe the number of items that they've put into their shopping cart. Things like this would be the state variables that we want to be tracking. Above that, we also typically want to know about the histories of these things, so we need trajectories. Where are these people walking in the store? And we may also instrument some of the, say, high-value items that are on the shelves and know where they are, too, if they're moving around. And you already saw this morning some of the work that we're doing, which is a very similar problem of tracking from video. Only this is maybe not surveillance video, but a lot of the same issues arise. And then the next level of analytics is event and activity recognition, and this is probably the most challenging level. Some things are pretty easy because we can have specialized sensors for them. So, say detecting when a customer enters or exits the store, or an employee. Each of those is probably not too difficult, although telling the difference between customers and employees might be a challenge. But think about trying to detect when a customer is waiting at the help desk and there's no one there to help them, or maybe counting how many people are in line waiting for attention, or detecting when a customer is looking for an item as they're walking down the aisle. When do they pick something up and maybe they put it back down, and so we say, that looked like something they wanted, but they decided not to buy it. Or they pick it up and they put it in their basket. Maybe we're trying to detect when a customer leaves the store without paying for the item. And then something that underlies all of this is building models of the system. So at the level of data cleaning, we use models of the typical temperature behavior or the correlations between multiple sensors. We might be wanting to predict customer traffic at the state variable level, and we might do that based on all kinds of things. We might know about current marketing campaigns, maybe the weather, the timing of the Super Bowl. All kinds of different things could be influencing this. Similarly, we might be wanting to predict supplier delays and understand our supply chain and how it affects the store, predicting price trends, and so on. So these are the sort of maybe non-real-time, but short and medium-term kinds of predictive modeling questions that we might have. And often we'll build models of those, and then those will feed back to support these real-time tasks. I should mention that I think in most of the work we do and have done in analytics has not been real-time analytics. And so for my field, that's the biggest challenge of the Internet of Things, is that we're getting data feed, one temperature reading every 5 minutes, maybe one video frame every 30th of a second, and we need to be able to be keeping up with that in real time and even getting ahead of it in some sense in terms of these predictions. So so far, I've only talked about the analysis hierarchy, and I did want to mention, and forgot to, that as we climb up this, we typically need our spatial and temporal scale increases. So we might be cleaning data at the level of one sensor or a couple of sensors, but by the time we're doing large-scale activity and event detection, we may be integrating all of the cameras in the store along with RFID tags and location sensors of the kind that Huaping Liu has developed, and so on. So that's another, the sort of data and computational complexity also climbs as we climb this hierarchy. But very often there are then bridges from analysis at various levels over to actions that we might want to take. So if we detect a broken sensor, then maybe we need to signal that the sensor needs repair, and maybe that's going into some tasking and scheduling system for our repair staff. A few years back, I had a senior capstone team trying to look at the data feed we get off of the Kelly Engineering Center, which is a LEED Gold building with lots of sensors on it. And we learned many things, but the number one thing we learned was how many of those sensors weren't working, 4 years after the building had been installed. So, yeah. Again, maybe at the level of state variables, we might be taking actions like incrementing a visit count. If we can recognize this employee, maybe from their affinity card or maybe from face recognition, we might then increment our count of the number of times they visited this store and update our model of their sort of loyalty and so on. At the level of events and activities, of course, is where there's the most interesting and actionable thing. So we might say alert an employee to go greet this customer because they are a high-value customer. Or we might detect, based on the behavior of the customer, that it's someone like me who's on a mission. I know exactly where the thing is I want. I'm going to get it and buy it, and I've only allocated 3 minutes to getting in and out of the store, and I don't want to be bothered by any salesperson at all. So, I think especially when you think about a store like Nordstrom's, where people are on commission, I think for each employee wants to be maximizing their effectiveness, and it would be very useful for them. I think they may make these judgments subjectively right now, looking at me, saying, "Oh, he's not worth the time." But also we might detect that a customer is having trouble finding something and alert an employee to help the customer find something. Or maybe we can, if the customer has a shopping app and they've actually built a shopping list, maybe we can interact with them over their phone and say, here's where each of these items is that you're looking for. Google shopping directions, that's what I want. Of course, there's a possible shoplifting event, cashier or help desk person needed, and of course, maybe we want to try to make some upsells or offer additional items to the customer while they're on site. Of course, there are many kinds of offline analyses, and these are actually more the traditional things that we have experience with in analytics, which are things like, predictive inventory management, predictive staffing, what predicts how long the customer will spend in the store, these kinds of things. But some of the opportunities that are opened up by having really pervasive video in the store or other kinds of tracking is we can see, well, where are there physical pinch points in the way we've laid out our merchandise? Where are hot spots where customers are likely to see something if we want to make a particular item prominent? Where are dead spots where customers are not going, or maybe they're even repelled from going? There's something undesirable about that. How can we change those locations? So analyzing just the trajectory data would be terrific for this. And as we've mentioned, when we're training employees, can we help them improve their conversion rate? And we want to also look at things from the customer satisfaction point of view. A lot of web analytics these days has really focused on maximizing click-through rate in advertising, right? So we have entire sessions in machine learning conferences devoted to online advertising and optimizing click-through rate. But it's really the wrong thing. You really, and people are now moving to the longer-term scale, which says, I want to maximize lifetime customer value of this customer to my enterprise. So let me think about what I'm doing on this visit that maybe doesn't pay off immediately, but makes that customer more loyal, more likely to return to me. I want to make sure, not that I upsell them to get the most money out of them today, but that I build a trust relationship with them, make sure that they get a high-quality product that will encourage them to return again. And so people are looking at in the web advertising space. With the Internet of Things, we can look at that in the physical space as well. Let's see, what else did I want to say? I think lots of interesting things that we could infer from video that are currently invisible in point-of-sale data. So when we see someone pause and look through a whole shelf, pick up a few items and look at them, put them back, and not buy anything, we know that there's an issue there with we're either not offering the right product or we're not offering it at the right price. And maybe we can actually talk to them while they're still in the store and find out what it was that they were looking for. Maybe we have it, but we just don't have it in the right place, and so on. So I don't want to focus entirely on retail. It was just useful to have a particular scenario. But let's think about a completely different vertical, which is personalized medicine. I think a lot of the same hierarchy exists and a lot of the same analytical questions. So ignoring for a moment the sensor question, we saw a lot of interesting sensors and sensor systems this morning. We have several state variables that we're going to want to be tracking. Say, if we have an Alzheimer's patient and we're interested in knowing where they are at all times, or maybe we're tracking various state variables of the person. We want the history of those as well, of course. And maybe we're looking for events and activities. I mean, obviously, we will often know about falls, although maybe not promptly enough, but can we get good measures of unsteadiness and other things that predict the risk of falls? Because we know falls in turn predict many other risks. Or breathing difficulties, things like this. Obviously, acute events, and then maybe for the younger crowd, these kinds of activities too. And of course, a lot of this here depends on building very sophisticated models. So we might need to know what is the normal profile of these state variables and these trajectories so that we can detect change detection being another huge thing. And similarly for gait, there are a lot of ways of using gait to detect neurological issues, for example. This is an instance of where we want to be doing anomaly detection or change detection, and to do that, you need to have models of what the normal behavior is of that person. And finally, of course, there are lots of exciting actions that we might take. If people are wearing glucose pumps or other kinds of medical devices, obviously we're controlling those in real time. But there are lots of exciting things happening in robotics with intelligent walkers or even exoskeletons. I hope to live long enough to take advantage of an exoskeleton to stay active even when I'm having trouble, maybe with unsteadiness and falls. And another vertical we might want to look at is smart buildings. I mentioned the challenges of the Kelly Engineering Center. But again, of course, we have lots of state variables, and in modern buildings, many of them are monitored or sensed, if the sensors are working. But there are others we might want to infer. So one of the things that we have a really hard time inferring is heat transport between adjacent rooms in a building, or airflow if I have my door open and my window open. Now, the Kelly Engineering Center knows my door is open and knows my window's open, but it doesn't have any kind of a airflow sensor that's right in my doorway. It'd be a little bit challenging. The events and activities, again, we have obvious things like the room is occupied or not, and in some of the classrooms, there are CO2 sensors that can give us an estimate of how many people are in the room. But what about special events? Maybe we're holding a reception for, say, 100 visitors today. If this were happening at 8 p.m. in the Kelly Engineering Center, we would probably be a bit cold because the system would have been cooling down the building at night. And we'd like it to somehow know that this is coming and not do that. Obviously, there are many other things we'd like to be responsive to besides the building itself. Now, buildings are very high-dimensional systems with all kinds of strange interactions between the cold side and the warm side, different stories, doors open and closed, things blocking events, and so on. And so we need to build models of how the buildings respond in order to control them. And we know this is generally done very badly these days. These are some of the kinds of things if we map to the building space. Okay, well, if we think now about, let's sort of step back and summarize what are the technology needs for a research to market Internet of Things center. So I'd like to just revisit basically 5 topics, well, and pull in a couple of additional ones. So first of all, we need data cleaning technology, and I've already talked a bit about this. But let me drill down a bit and say there are really 2 separate problems. One is recognizing known failures of sensors. I mean, if a sensor flatlines, it doesn't take a very sophisticated statistical model to figure out that something is wrong, right? But the thing is that sensors out in the physical world, particularly perhaps if they're under cyber attack, can fail in novel ways. And so you can't rely just on a sort of disease diagnosis mindset that says, well, there's 12 ways this sensor can fail, I just have to figure out which one it is. And so for that, we've been doing a lot of research here in anomaly detection. So I obsess a lot about the unknown unknowns and how our existing techniques tend to assume that they have complete knowledge of what are the relevant variables, when in fact, I think all of our systems need to be open to novelty at all levels. And let's see, I guess another thing I want to call out is not only have I been assuming that all the sensors in the network are working, I've been assuming that I have infinite data storage and it takes me no time at all to access it. And so data management and particularly fusing data from multiple diverse sources, from different generations of sensors and so on, this is a huge challenge. So I list some of the names of the people here that are working on these things, and particularly want to say how glad we are to have hired Arash Termechi because he's really helping, particularly in the data management area. The next thing, of course, is computer vision, and we've discussed all kinds of things that we would like to be able to do with computer vision. And Alan Fern mentioned in the football context that some of these are quite difficult. Those are all research challenges, pretty much. I mean, we have face recognition now with Facebook when you upload your pictures, but we're beginning to have object recognition that spans, say, 15,000 or 30,000 different kinds of objects. But they're pretty much at the level of chair versus car versus table, as opposed to which brand of, of microphone you're holding or something like this. So there is a challenge, a computer vision challenge, to take the catalog of Amazon and try to recognize all the objects in the Amazon catalog. And I know my friends from eBay have a similar challenge. The eBay guys actually have the advantage that every day thousands of people spend hours photographing objects and labeling what they are, and then telling eBay about that. And so they claim to have the largest labeled image database in the world. So we can see that we can imagine all of these different specific kinds of items and or events and actions, but also maybe trying to make assessments of emotional state or it's sometimes called sentiment analysis in text, right? Is this person frustrated? Are they impatient? Are they angry? And this will also be very useful for us. Modeling, this is a very broad area, but discovering interesting patterns in data, integrating external data sources, because very often we'll know quite a lot about our customer, not only their customer ID, but maybe their website visits to our website, maybe to third-party websites, maybe to social networks. Maybe they're using a shopping app that we're owning or participating in, and using all of this to take actions that really meet the needs of the customer is a challenge. And obviously another task where I think analytics needs to reach down to the device and system and networking level is optimizing where and when to compute these real-time analytics. The picture I painted so far makes it sound like we suck all the data off the sensors and stream it all to some giant cloud-based system where we're doing the analytics. But for example, if you're doing anomaly detection, you could push down to each individual sensor a model of what you're expecting it to be reading. And it can check right at that point of measurement whether it's matching the model and only report excursions away from the model, and so you can use that to do very smart coding and compression of the signal, as well as to offload a lot of the computation that might be happening in the cloud. Another huge issue is interactive information visualization, and you saw a little bit of that with Ron Matoyer's talk, but this is a big area for. If we're looking at trajectories, we're looking at time courses of events and so on, visualization is a huge challenge. So we have several people who've been working more in this general area. Margaret Burnett mentioned some of the challenges of the user interface and the user experience, but I think this is a place where we need a tremendous amount of work. I mean, there's simple things like if we're really going to have some way to queue an employee that they're needed, besides saying, customer waiting at the bottle return, what should that be? What will be the most appropriate way? But also, is the customer really going to want to interact with their phone while they're walking through the building? What are going to be the ways that are really useful to the customer and are not creepy to the customer? I mean, I want, if I'm sharing my personal information and being watched by you, I want that to be a friendly experience that meets my needs and not view it as an adversarial relationship where you're just trying to sell me stuff that I don't want, right? So how do we build that long-term customer relationship, and what is the long-time customer experience, and how do we optimize that? And I think there's a similar question for our employees. How do we make them full participants in improving their own effectiveness as employees, and feeling that they're part of a successful man-machine system in a way? Now, of course, another thing that I think is a complete showstopper for all these systems is security and privacy. I've just been recently dealing with a lot of the stuff in the press, remarks by Stephen Hawking, Elon Musk, about the risk that artificial intelligence might take over the world. And I think those are interesting kind of science fiction and philosophy scenarios, but a much more concrete problem is cyber hackers hacking into our self-driving cars, into our power grid, into our sensors, and actually modifying the data coming out of the sensors so that we don't see the guy who's stealing the high-value object in the store because he's not in our video or he's eluding all of our sensing. So I think security is going to be make or break for all of these systems, and it wouldn't surprise me. I believe that in our immune system there's something like a 90% overhead in terms of the amount of molecules that are involved in detecting diseases versus the amount of molecules that are involved in keeping the immune system successfully operating. Maybe we're going to be facing something like that with computing and security, where there's maybe more than a 50% overhead just devoted to checking that the vision I have in my mind is that I have this nice little cell phone in my pocket, and then there's a supercomputer behind the screen that's checking to see that it hasn't been compromised. I hope we're not to that point, but it sort of feels like it these days. So of course, a lot of cybersecurity is really a failure of software engineering and testing to make the systems tight that way. But we also obviously have issues with encryption, with ensuring privacy, and we've been doing a fair amount of work with the federal government on using anomaly detection and other things to try to deal with computer intrusions and other kinds of attacks. So again, you've heard from several of these people today, but it's a huge priority for us. And the last thing I wanted to talk about is the need for kind of executive control of the entire system. I mean, partly this is because we want to ensure an excellent experience for the customer and the employees, so we don't want every different component of the system to be able to send alerts to their handheld device. I mean, we're already seeing the kind of chaos that arises on our phones now that the alert screen is becoming prime real estate, and it just makes all those alerts turn into noise, and the customer will ignore them completely. So the whole human-computer interaction world is still stinging from the Microsoft paperclip experience, and we want to not be clippy. We want to really optimize the experience for the customer. And at the same time, of course, we have many other optimization objectives: power, bandwidth, the cost of doing the data analysis itself, profit and loss, and so on. So there's quite a lot of people in EECS that work on optimization and planning, and even reinforcement learning. I was at a meeting, which is a form of machine learning in which you're not shown the right answer, you just get a penalty or a profit signal. I saw a talk from a guy from the Technion in Israel 2 weeks ago on what I call a nagging app for diabetes management, right? Where the system is monitoring blood sugar, and then it can send the patient either positive, encouraging messages or scolding messages, or send them to the spouse. And so they did a field deployment of this, and then the system learns from interactions which strategies actually work best. And surprise, surprise, sending nagging messages does not work. Very rarely. The optimal policy that they found by applying these algorithms was to send positive feedback to the patient. That's number one. At a lower rate, send positive feedback to the spouse, and only very occasionally, when it's extremely serious, do you send a negative message to the patient, and never to the spouse. So and they're measuring this in terms of long-term compliance with the protocol that the patient is on. So why work with Oregon State? I mean, we are leaders in things like mixed signal circuits, in machine learning, artificial intelligence, data analytics. But of course, as the airlines say, we know you have a choice when you're thinking about research partnerships. I think some of the things that we've built here are quite unusual. The very tight coupling between electrical engineering and computer science in our School of EECS is not that common. There are many joint CS-EECS organizations. Berkeley, for example, comes to mind. But I know, since a friend of mine was department chair there, that those are two very different and separated worlds, whereas here we have many collaborations across the divide. And in fact, I sometimes have to go to the website and say, what's this guy's training? I don't remember whether he's a double E or a computer engineer or what. Another thing is we have consistent federal funding. We're very successful there. And so you're able to leverage those funding sources working with us. We also have a strong entrepreneurial culture, and you heard a lot about that this morning, so I won't belabor it too much. But I will mention that we have close ties with the College of Business, because Engineering plus Business forms the Division of Engineering and Business at Oregon State. And there are many easy routes to collaboration with industry. We have standing intellectual property agreements with some of you, and we'd love to have more of those. So let's do it.